Welcome. We're going to talk about logarithmic functions, how it all fits together with what we know so far and where we're headed. Logs certainly come in handy for a number of things, and hopefully this will start to shed some light on some of those things. So basically, logarithms and exponents are inverses. So if you look here at this blue graph, we have the graph of y equals 2 to the x, which is that exponential function that we've been talking about with an asymptote of the x-axis. And as you know about inverses now, that is a reflection about the line y equals x. So we have the line y equals x, reflect that over, we end up coming up with a graph of the log base 2 of x. So logarithms and exponents are inverses. When we look at that from an equation standpoint, we have some equation b to the x equals a. B is the base, x is the exponent, and that equals some value a. We can rewrite that as a log expression. The b stays the base. We'll have the log base b of a equals x. So I think it's probably easier to see it going from this log equation. So if we're looking at the log equation, and log base b of a equals x, it's really saying b to what power equals a. So if we go from that log back to the exponential, b to what power equals a. Here's a few different examples of going from an exponential equation to a logarithmic equation from just from one form to the other. So 2 to the 6th power equals 64. We know that. Another way to write that in logarithmic form is log base 2 of 64 equals 6. So that's saying 2 to the 6th equals 64. And there's just some more examples here. 4 to the 1st equals 4. In logarithmic form, you'd write that as the log base 4 of 4 equals 1. 5 to the 0 equals 1. We know that as well. To rewrite that in log form, log base 5 of 1 equals 0. And we have 5 to the negative 2, and so on and so forth. So as we go through, there are times when we'll have a variable. So 3 to the x equals 81. To rewrite that in logarithmic form, log base 3 of 81 equals x. That's like saying 3 to what power equals 81. So from logs to exponents and back again. So if we were to rewrite these in logarithmic form, we have 9 squared equals 81. The base stays the base. So that should help when you're rewriting these. So this is saying the log base 9 of 81 equals 2. Log base 9 of 81 equals 2. So this means 9 to the 2nd power equals 81. Just another way to write it. Same thing here. 3 stays the base. So the log base 3 of 81 equals 4. 3 to the 4th power equals 81. That's going from exponential to logarithmic form, and you can do the same thing going from logarithmic form to exponential. Log base 2 of 16 equals 4. That's the same as saying 2 to the 4th equals 16. Log base 1/2 of 8 equals negative 3. That's the same as saying 1/2 to the negative 3 equals 8, which it does. So log base 1/2 of 8 equals negative 3 is the same as saying 1/2 to the negative 3 power is equal to 8. So some special properties of logs, which we probably don't even need to think of as special properties because it just makes sense. If you have the log of any base, log base b of b equals 1. That's regardless of what base you're going to throw on there. But if you rewrite that, that's just rewritten in exponential form as b to the 1st equals b. So it's really nothing earth-shattering about log base b of b being equal to 1, because if you rewrite it, it's going to work out. Same thing for the logarithm of 1. Log base b of 1 equals 0. That's really just because b to the 0 equals 1. Anything to the 0 power equals 1. So I wouldn't spend too much time thinking about these as special properties, but I do want to point out this chart if if you're going through your book and you see it kind of jumping out at you. It's really just that same thing going from logarithmic form to exponential. when there is a logarithm with a base of 10, it's called a common log. So we generally don't write the 10 when we have a base 10. For, as you see in this example, log of 5 equals the log base 10 of 5. So that's the same thing as if we had the log of 8, that's really just the log base 10 of 8. So if you don't see any number written in the base, it's a 10. Log base 10 of 8. So going with that same idea of how this goes from one form to the other, oftentimes it's easier just to think of these logs in terms of using mental math. So if you have the log of 1,000, there's no reason to grab your calculator and start typing things in. You know that that's a base of 10. So if it's base 10, you're really just thinking 10 to what power is equal to 1,000. So you don't need to grab your calculator because you just need to know what 10 to what power is equal to 1,000. So in this case, that's going to be 10 to the third power. So that's going to give you 3. Over here with the log base 4 with 1/4, that again, that's like thinking 4, the base, to what power is equal to 1/4. Well, what will allow you to take 4 and send it to the other side of the equation? You know it has to be a negative, and in this case it's just a -1. So no sense grabbing the calculator and trying to figure out how you might deal with a base of 4. A lot of times just by switching the form, it's going to make sense and really shed some light on what the answer would be for that log or exponent problem. The logarithmic scales are used for many things. Measuring earthquakes with the Richter scale. We have sound with decibels. Those are all logarithmic. We have the acidity of different things going from, lye to acid. So we have something very base-like and very acid-like. And also the CSI type of crime solving, when they say that a body was killed between the hours of 2 a.m. and 4 a.m. and how they figure that out, that is based on Newton's law of cooling, which really just uses logarithms to come up with the answer to those crime-fighting ideas. So there'll be more on each of these things and logarithmic scales and what we can use them for in one of the upcoming exciting episodes of Logarithms. Have fun. Talk to you soon.